start with a tiny anecdote that I'm still very grateful to Stefan to hiring me 12 years ago with 0 database papers. So that was, I'm still very grateful to this day because otherwise, none of this would have happened. Yeah, today I'm really excited to talk to the family reunion. It feels a bit like it. Everyone's here. It's really exciting. I've been given a lot of talks the last couple of years, but this one is I was a bit nervous because I thought, okay, Andy is going to be here. I better not say anything stupid. But let me get started. So I want to talk a bit about the two-tier architecture. But before, I want to sort of motivate why I care about database systems in the first place. This is a tablet from Uruk that was excavated in It was made in 3000 BCE. That's not before Cod, but the other C. It's a 5,000-year-old table. If you squint, you can see it's a table, and it's interesting because we've had tables about 1,000 years before written text. Okay, so this is a fundamental civilization technique, and this particular table is close to my heart because it accounts for amounts of hop and barley, and we don't know what to make of this. So. But it's just something that really gets me excited. So very briefly after this tablet, people started building relational systems. And this is a picture from Felix from HPI who made this genealogy of database systems. And I think, obviously you can't read it from back there, but you can see a certain sort of lininess to it, right? And that kind of tells you that relational systems never die. They still going strong no matter what the MongoDB consultants say. And they really are a fundamental pillar of our civilization. You can't run a company or a country without them. And yeah, so this is just one of these eternal technologies that, like operating systems, they're here to stay. However, despite we all agreeing that databases are super important, other people disagree. So here's Hadley Wickham, a leading light in the data science world, saying if your data fits in memory, there is no advantage of putting it in a database. It will only be slower and more frustrating. And we saw this years ago, and we thought we need to do something about this. We can't let this stand that the world hates the things we love. And so this, among other people in the data science world, were kind of the trigger for us to start working on a new relational database system that was trying to work on the frustrating bit. And I'm happy to report that Hadley and his company are at this point customers of DuckDB Labs. So we managed to convince him. But the frustrating bit is actually hitting on something really important. So I think, not the people in this room, but the people out in the world generally fear data. Because everybody knows how to operate Excel, right? But once the things don't really work out so well in Excel anymore, people have a general fear, I think. It's like, what on earth am I going to do? I'm going to install Spark. Am I going to install Postgres? What is it? I'm going to go on the internet and Google, what do I do with my data set? And this is really I think it's a feeling of fear and uncertainty and doubt and all these choices. And this is actually true because the common tools that people use can be unwieldy, clumsy, sometimes totally hostile, right? I have installed a lot of database systems out there for testing purposes, and very often I have felt that they were being hostile. And the reason for that, in my opinion, is because database systems, they tend to be sold on the golf course. One CEO talking to the other CEO, not necessarily the technicians talking to each other. So it's totally fine for them to be hostile. But we want to really enable this confidence for people working with data. We want to change that. We want to get rid of the fear. Don't fear the CSV. Enable people to actually do something with data. And we think we have really just scratched the surface in this. And it's been mentioned, Mark and I started thinking about what an analytical data management system could look like. The result is DuckDB. It's a relational system in a way. It's very traditional. So when I first talked about DuckDB to Martin and Short, I think Short is somewhere. Where is Short? There's Short. He basically said, "What's new?" And he was right because it was not really new in many ways. It had tables, it had SQL, it had columnar storage, But in many ways, it was very different, namely with this completely different approach of trying to really enable people and lowering the barriers of entry of data. So I will go a bit more into details on the decisions, the architectural decisions of DuckDB, and then come back to this question of the two-tier architecture. Okay, so hard decision time. And I mean, many people in this room will know this hard decision time. Let's say you want to build a new database system. There's a lot of hard decisions to make, right? The first question is, should we make it distributed? And as Stefan has mentioned, I did my PhD thesis on distributed query processing, and then came here and thought, we'll do something distributed. And then that's really, I think also maybe 15 years ago, it was really the ultimate wisdom to say, no, it has to be scale out. Then there have been some detractors, right? The people who are doing all scale out, and then these detractors from Switzerland come and tell you that this is not a good idea because some sort of cost issue, I don't know. This is still one of my favorite papers out there where they basically show that lots of the graph algorithms don't really benefit from being distributed. But at the same time, and this paper has already been a couple of years ago, at the same time we've been seeing this extremely crazy development in CPU capacity, for single node capacity. So now this laptop has like 16 cores. It has 400 megabytes of CPU cache. It's totally wild if you think about it. This is like a hardcore server machine from 2010. It has 400 gigabytes per second of RAM throughput, and I think this one doesn't have 128 gigabytes of RAM, but you can have 120 gigabytes of RAM. Totally wild. Completely unthinkable 10 years ago. Similar to SSD, similarly we have now SSDs, storage devices that are a complete game changer for data because of the high speed. For example, this one has this laptop has something like 5.5 gigabytes per second in data access for the SSD. And DuckDB, of course, we'll come back to that later, can make use of these things, but what does this really mean for data? And I have a chart, okay? So this is very scientific, okay? We are at the CWI. I have a chart. So here we have a chart that says, okay, we have the past, we have today is today, we have the future. And the line here says, what is the yellow line? It's 99% of scans. These are 99% of the scans, the reads of data people do. I'm saying scans and not data set because people love to claim, it takes a great man to admit that the data is small. People love to claim that the data is massive, but with columnar storage, like Parquet files, we actually don't read a lot of this stuff. We have early elimination of partitions and that kind of stuff. So the scans are really what is being read. So 99% of scans. And this blue line we have now is the single node capability, right? In the past, we had a very slow single nodes. We couldn't do 99% of scans. And now, as I've tried to show, the single nodes have been getting better. And the distance between single node and the 99% of scans has been shrinking, right? With the hardware getting faster and data sets not really growing at the same rate because the amount of humans we have on the planet doesn't grow the same rate as the MacBook Pro CPU. It's true. So there is this data singularity, right? There's this point in time where 99% of scans will be totally feasible on a single node. And when we started with DuckDB, that was really the hill we were going to die on, we thought. But the world has somehow agreed with us in a very quick way. So here's a picture from a blog post from George Fraser from Fivetran, who, by the way, are also big users of DuckDB. They analyzed public data from Snowflake and Redshift about the workloads, and it basically showed that the plot displaying the data scanned for queries that scan at least 1 megabyte. And the median scan reads 100 megabytes of data. And the P99.9 is under 300 gigabyte. So, this kind of territory. So we might actually already be there with the data singularity. This is, we already can do 99.9% of scans on a single node. Interesting. So our decision time for our database system went for the single node, right? The next question is, what kind of execution engine should we use? Thomas has shown conclusively that the best performance for query engines can be gotten with just-in-time query compilation. However, it's difficult. We are not clever enough for that. And it actually is kind of difficult to get in a portable way. So we went for, vectorized query execution, something that Martin and Peter and Niels is also here, he's hiding in the back, have invented here at the SWI. And it's been shown to be generally performant enough, let's say. I want to complain about one thing, though. I want to complain about computer scientists naming things. Like, why on earth could this not have been, why call it vectorized query execution, right? So I think they have the perfect name here, hyperpipelining, personally. But it's just such a missed chance of naming things. I'm not happy about calling it vectorized execution, but that's what we have. And for those of you who have not been paying attention, what is the vectorized query execution paradigm? Well, it basically changes the intermediates between query operators in a query pipeline from looking at one tuple at a time to looking at many tuples at a time. And those are going to be in columnar format. This amortizes the interpretation overhead. You don't really need a JIT to get good performance, and in generally displays well with the CPU cache. So this is great. This is really a wonderful method. We have been very happy with it. But once you start working on this, and I just wanted to give you some sort of insight into the things that we've been up to, because you would think, what have you done? You just looked at the paper and implemented it. That's not necessarily true, because it turns out vectors are not all vectors are entirely equal to each other. We want to have something like compressed execution. However, we cannot really generate the code for all variants for compressed vector representation, for all the operators in our systems, for all the, the expressions, for all the, the addition, the multiplication, and so on and so forth. That would actually lead to a gigantic binary, and it's not great. So this combinatorial explosion of operator, data types, and compression formats has to be managed. And the way we manage it is with this unified representation. So this is a slide from Andy that we stole back, because he stole it from us and we stole it back now. He changed the colors. You also got it wrong, because this was switched around. But so together with Ori Erling, we came up with this idea of the unified vector format, where we have this cheap translation from the compressed representation of the vector. So here on the left, we have the uncompressed area, which is the flat vector. We can have compressed things like the constant vector, or we can have a dictionary encoding. And we define this cheap translation to this unified vector format, which essentially consists of a data array and a selection vector, which basically points into this data array. And that's really nice, because with this, we can ship a high-performance query execution engine, because the actual individual operators can get pretty good performance by just looking at this unified vector format. And with this, we can make this engine that really works well. We can make a state-of-the-art query execution engine with compressed execution that has a manageable binary size, is highly portable, easy to understand, and so on and so forth. So really nice. So we went for vectorized. And now I have this terribly looking slide. I apologize. But I wanted to just give you an idea of the other long list of sort of decisions that you have to make when you make a new database system. And it's really been an interesting sort of thing. And let me briefly go through them, right? The first one on the top left is AVX 512. One of the things that I'm personally not too happy about in database research is people jumping on the, whatever latest, instruction that Intel, may they rest in peace, comes up with. And then we spent 5 years of daemon workshop on optimizing for this one thing, and then turns out we go for ARM after all. So I feel like that's just so sad in sort of a intellectual power sort of but no, we didn't do AVX 512 explicitly. The compiler sometimes can generate them because it's hell for portability, and it turns out we go on ARM anyway. There's other things like the exchange, the parallelism paradigm, right? We have traditionally have exchange operators, while we have seen that there were some really big issues with them, not only on NUMA machines, so we went for morsel-driven parallelism. That's something that also Peter and Thomas have worked on. We have concurrency control Obviously, traditionally this will be pessimistic, but for analytical systems, we will use optimistic control. Licensing, MMAP has been shown to be dangerous. GPUs, yes, thank you. Great paper. I've reread it like last week because I thought, this was fun to read, and it is fun to read. We have like GPU versus CPU, right? This is this wonderful. Another thing that VCs love to throw money at is like GPU-based databases. I think that's generally not a good idea, so we went for CPU only. We didn't write it in C, we didn't write it in Rust, we went C++, kind of in the middle, I would argue. We didn't do client-server for various reasons. There's a wonderful paper. And as has been discussed, we didn't go for NoSQL, we went for SQL. Because I think fundamentally you can really only revolutionize one thing at a time. So we basically said, okay, we'll make this thing easy to use in a small package, single node, and in process. That's kind of enough sort of radical sort of thing there. We should probably leave the rest alone, because if something has been working for 20 years, probably it's a good idea. Okay, so this is all the decisions that we had to make. Not all of them. Some of the decisions that we had to make. But I want to do a little bit of a deep dive in one current research direction that I'm personally very excited about. And that is out of core. So I have to explain. So here we have the SSD again. If you're going to go for single node, right? The resources that the single node have are going to be limited by definition, right? This is the box that you have. So if you're running out of memory because the user just invents a big Parquet file, you can't just say, oh, sorry, right? Because you don't have anywhere to go. You have a single node. On the scale-out systems, you can say, we'll just add more machines. We can't really do that. Buy a bigger laptop. It's a bit of a hard sell. There's a sort of error message. So we really went all in on out of core, where we can make use of the disk in the computer for the intermediate results during query processing. And again, this has 5 gigabytes per second of I/O speed, so it's probably pretty good. And thankfully, we have Laurens. Laurens is here. He's one of our team members in DuckDB. He loves disks. Okay. Laurens loves disks. And he's either the best friend or the worst enemy of SSDs, because obviously with his shenanigans, he decreases their lifetime, I think. But in the same time, we solve data problems and we reduce fear of data. It's a good thing. And so what he's been working on for the last couple of years is how to basically redesign algorithms or operators in query pipelines so they can scale beyond main memory on single node. Because the current situation is very often that we have the scaling behavior of existing systems that as we crank up the dataset size, the execution time kind of grows normally, like linearly, expectedly. This is log, so. But it grows in sort of a predictable way until we hit this memory limit, which is this dashed line here. And then one of two things happens. Either we crash, somebody crashes, or we get this giant step in execution time where basically the database system has to switch to a different algorithm to do something. And we don't really want that. So here's an example on why this is an issue. So say we are scanning a terabyte of customer data here in this left pipeline 1. And let's say we have a very sort of uncooperative join that's basically joining on the customer ID, which is pretty unique. So now we have scanned 1 terabyte, but because the join is a blocking operator, we have now built a hash table. That's also 1 terabyte. Wonderful. Now we move on to pipeline 2. We scan another table. We probe the hash table we just built. We do some projection, and now we do a group by build. Again, we're grouping on an uncooperative key. Now we have another terabyte of hash table sitting there. In the worst possible moment, just before pipeline 1 finishes, we have now 2 terabytes of, just before pipeline 2 finishes, we have now 2 terabytes of stuff sitting in main memory. If we have 1 terabyte of RAM, or this one doesn't have a terabyte of RAM, if we have a couple of gigabytes of RAM, we are kind of out of luck. So how are we going to solve this? And I'm just going to show you 3 operators on how this can be addressed. So here, this is one of Laurens' papers. This is about the sorting operator, which is one of these core operators that everybody tends to forget about. And basically, the idea is that we have individual threads that make these sorted runs using either PDQ sort from Orson, who is here, yes, or a radix sort. We make these sorted runs, and then there's a really cool optimization called merge path, which figures out where in these partitions the merging should take place. And that's something that can happen individually by sort of worker threads, with other things being able to be pushed out of RAM in the meantime. And so basically, with this method, we can make this sorting work basically with an arbitrary amount of memory, while still being, using memory as much as we can. And with this, if you do all this, you get these kind of results where you ran a sort on these various systems there, and basically as you crank up the amount of rows, the execution time grows, but you can see that in this case, DuckDB will be doing very well in the execution time, simply because it's able to gracefully degrade the amount of RAM, the resources used, and be able to use the disk. I have another picture to confuse you. This is the similar approach, but for the aggregates this time. And here, again, the trick is that we will not give up the hash aggregate entirely, but instead use partitions to reduce the memory pressure at the point in time, at the worst case point in time when we have to finalize all these things together. And again, this will work really well when we run experiments on this. And I have one more. And finally, we have the join, sort of the holy grail, right? And I'm happy to report that the paper that we wrote on this together with Paul and Peter, who are also here, it's a family reunion, I'm telling you. All the authors of all the papers I've ever read or written are here. It's a bit strange. This has got a revision last week, so basically here we have the join. And it's really interesting because it sort of revives a method from ancient database history, the Grace join, and the hybrid hash join, where basically we can partition the join and then use this clever trick of overflow, where if we don't have to put the entire hash table into RAM on the probe, if it doesn't entirely fit, we'll put a part of it in RAM, and then there might be tuples that don't match the parts that we have in RAM, and those we have to store in an overflow, again on disk, and so we can read them later. And again, with this trick, we can make this really work for really big data sets on really small memory. But I've showed you some sort of internal tricks that we can do in DuckDB, but I think what we're kind of missing is a bit of some sort of discussion on what this actually means for computing architecture. And that's kind of where I want to go next. We have this execution engine now that's fairly small, that's fast, that can go do a lot of things on single nodes. But what does this actually mean for architecture? So let's look at the standard two-tier architecture for analytics. We have the database, very nice, stack of disks, and we have some clients talking to the database. That's wonderful. And then sometimes we have a three-tier architecture, because people love drawing things in MS Visio, where we have an application server that runs some sort of application code, and then that talks to the clients, and then the application server will talk to the database as a sort of single point. Very often, the data has to come from somewhere. We have operational databases here on the left that regularly have some batch job that ingests everything into the data warehouse. Important term. Okay, and that's how sort of things generally went for millennia, right? Maybe, and maybe throw one or two Kafkas in there. I don't care, right? It's really doesn't really make any difference anymore. And then, of course, things happened, and we have a data lake instead of the warehouse. It really changed not a whole lot. We have the data lake now, and we gained a Spark cluster. Okay, the rest is pretty much unchanged. But now let's imagine what actually local execution can mean for this general picture, right? And I think it's really something that we haven't seen a lot of. I mean, we have seen some things, but we haven't really seen where this can go. So enter DuckDB. There's no reason we cannot put an analytical engine in our sort of operational databases to basically maybe run some Parquet exports for us. We can pre-aggregate, pre-filter, pre-enrich, and so on. We can directly push this into the lake onto S3, no problem. Maybe we'll use, instead of the Spark cluster, we can use a lambda to transform data because we can run DuckDB in a lambda, a couple of milliseconds of startup time and highly efficient implementation. Really works well. We can put DuckDB in the app server, for example, or DuckDB is a stand-in here. I'm not really talking about it has to be this particular thing. We can put polars in the app server. It really doesn't matter. The point is the architectural implications of these kind of things, because we had this, in the past we were just so used to the database sitting on this giant server. Now this is no longer necessary. Let's put it on the app server. The data transformation can be part of serving app server requests, great. We can put DuckDB into desktop apps. We can put DuckDB in the browser with WASM. We have really great latency for data transformations. We can put it on phones. We can put it on, all sorts of funky devices. And that really is an interesting sort of thought, right? Like what happens if we suddenly have database engines just running everywhere? What does this mean about application architecture? There's currently a research project here at CWI running where we think about the privacy sort of implications of running local data. Super interesting stuff. MotherDuck is doing things with hybrid execution, which takes us even further, where part of the query is running in one place, part of the query is in another one. I won't go into much detail on this. We are seeing people putting DuckDB in satellites. We are seeing people putting DuckDB into cars. And I think it's really interesting, the question, where can this all go? And I think it's, as I've tried to show earlier, it's really credit to the simplicity of the vectorized design, because it enables a small yet fast engine. Okay, I have 10 minutes, and I thought I couldn't really come up here and give a talk about databases without experiments. So we will carry on with totally unscientific and unpublished experiments. And this is a bit of a, I thought you're the first people to see this. So this is really a world premiere. Well, this one is you're not the first people to see this one. This is a picture of the results of TPCH, a scale factor 100 from the original X100 paper. It ran on something called an Itanium. And me being young-ish, I didn't know what that was. So I asked Peter, and he said, this is the Itanium. And apparently, so this is the, I think it's the picture of the actual system that you had. Yes. Thanks for Peter for having it. Amazingly, Peter even still had the invoice for it. And it's running something called an Itanium, which used to be was the pride of Intel in its high day. Single core, 1.3 gigahertz, 3 megabyte cache, and as far as I know, the paper says running with 12 gigabytes of RAM. So this was, if you look at these numbers, this was what they used for the paper to, show this radical new execution model. So what are we going to run this against? iPhone. So we got the latest iPhone. We have since returned it because I don't want a new iPhone. We got a new iPhone. iPhone 16 Pro has an ARM chip, 64 bits, 2 fast cores, 4 slow cores, up to 4 gigahertz clock speed. It's been 20 years since the Itanium. It has many AI features, I have to note, and a GPU, but we completely ignore. And here are the results. So turn out DuckDB on the iPhone can actually almost match the X100 results on the Itanium. And it really is the credit to the vectorized query processing paradigm that it's a world away in hardware, it's a world away in software, and still manages to perform really well and to take a lot out of this hardware. I have to admit something, though. In order to get this to work, we had to do something we now call very cold runs. Because the thing is, the iPhone has this annoying thing that if it gets warm, it clocks down, and running TPCH gets it warm. So we got a box of dry ice, and to keep it from clocking down due to overheating, it's minus 50 degrees. We measured it. It turns out phones are not really built to run database benchmarks. Who would have known? The phone did die, but came back to life. And if we had read the manual, we would have known this, because it says your device could turn off, and it also says that cold temperature might affect the performance of your device. I think they meant it the other way around. Of course, it made it faster, so that's very nice. And just last night, Gabor, where's Gabor? Gabor called us out as the hopeless Apple snobs that we are, and reran this with the latest Samsung phone, S24 Ultra, also has AI, I'm happy to say. And that was much faster, and there wasn't any dry ice required. But this is just, I think it's just such a wild thing to say, and I want to go back to this picture. Of course, we're having fun with freezing iPhones, but the point here is that the architectural implications of running like serious data processing engines on things that you have never even considered putting databases onto, I think are profound. And I really want to encourage you to think about new and exciting places you can put a data engine on and what that would mean for applications, for a general software stack, for maybe efficiency, for resiliency, maybe for privacy protection, for all these things. Where do we go from here is unclear, right? We have not even scratched the surface. And the data management technology is no longer shackled to the data management sort of server cluster. And it's, in large degree thanks to Marcin's work here at SlipEye. And where will databases go next? I don't know. We'll see, but that was it, and thank you very much.